The night of January 1, 1978 was clear over the Arabian Sea. Air India Flight 171, a brand new Boeing 747, had just taken off from Bombay's Santa Cruz Airport, bound for Dubai. Captain Madanlal Kukar, an experienced pilot, was at the helm. Moments after takeoff, the plane began an inexplicable turn to the left. Inside the cockpit, confusion turned to alarm as instruments gave conflicting information. The primary attitude indicator likely malfunctioned, misleading Captain Kukar. The co-pilot, Indu Vermani, tried to warn the captain, but his warnings were not enough. The Boeing 747 continued its descent, a terrifying fall toward the dark waters below. For the 213 souls on board, the final moments were a blur of confusion and fear. The plane, in the air for just over a minute, was now in a steep, irreversible dive. The pilots fought for control, battling against a machine that was no longer responding. The end came swiftly and violently as the Emperor Ashoka slammed into the sea. The impact was catastrophic, disintegrating the aircraft instantly. There were no survivors. Witnesses on the ground saw a flash of light on the horizon, followed by a deafening explosion. The new year began with a tragedy that would send shockwaves through the aviation world. The investigation would uncover a simple mechanical failure, but decades later, a deeper possibility would emerge, challenging everything we thought we knew about aviation safety. The initial investigation into the crash of Air India Flight 171 pointed to spatial disorientation. The captain's primary attitude director indicator had malfunctioned, leading him to believe the plane was banking right when it was actually banking left. This explanation was widely accepted for years as a tragic case of human error compounded by mechanical failure. However, as technology advanced, experts began to question this conclusion. The Boeing 747 had multiple redundant systems. Why would a single instrument failure lead to such a catastrophic outcome so quickly? Investigators started to wonder if the problem wasn't just a broken gauge, but something wrong with the digital brain of the aircraft itself. This new line of inquiry was about understanding a deeper vulnerability. The investigation was unofficially reopened by scientists and engineers, looking for a hidden factor that could explain the bizarre behavior of Flight 171. Recovery teams worked tirelessly in the waters off the coast of Bombay, piecing together the final moments of the Emperor Ashoka. The wreckage was fragmented, evidence of a high-speed impact with the water. The initial focus was on the cockpit instruments, particularly the captain's attitude director indicator. When recovered, it confirmed the original theory of instrument failure and pilot disorientation. The black boxes provided a chilling timeline of the disaster, capturing the confusion of the pilots. But they didn't fully explain why it happened so quickly and without correction. As scientists delved deeper into avionics and computer systems, they began to see the story differently. They looked beyond the mechanical failure and started to examine the digital systems that controlled it. The Boeing 747 was one of the first jumbo jets to incorporate sophisticated computer systems. These systems were supposed to make flying safer and more efficient. But what if they had a hidden weakness, a vulnerability that no one had anticipated? This new perspective shifted the focus from the physical wreckage to the invisible world of software and microchips. The story of Air India 171 was about to be rewritten, with a new chapter far more terrifying for Boeing and the entire aviation industry. Years after the crash, a team of independent researchers re-examined the data from Air India 171. They noticed a tiny glitch in the data stream, a digital hiccup occurring just before the first signs of trouble. This anomaly was a bit flip, where a 1 becomes a 0 or vice versa. In a highly sensitive system like an aircraft's flight control computer, a single bit flip could have catastrophic consequences. The researchers hypothesized that this bit flip was caused by a cosmic ray striking a memory chip in the flight control system. This event, known as a single event upset, was a known phenomenon in spacecraft but not considered a significant threat to aircraft. It suggested that airplanes could be knocked out of the sky by invisible particles from space. If correct, it meant the crash was not just mechanical failure and human error. It was a sign of a fundamental vulnerability in the digital technology rapidly becoming the backbone of modern aviation. The implications were enormous, suggesting every computerized aircraft was potentially at risk from a cosmic event. The puzzle of Flight 171 was shifting from a simple mechanical problem to a complex scientific mystery. The theory that a cosmic ray brought down Air India 171 was shocking. Cosmic rays are high-energy particles from distant cosmic events constantly bombarding the Earth. At high altitudes where airplanes cruise, the atmosphere is thinner, and radiation levels are higher. A cosmic ray could have struck a sensitive memory cell in the Boeing 747's flight computers. This event, a single event upset, would have been instantaneous and invisible. The cosmic ray could flip a single bit of data, corrupting a crucial line of code. This discovery introduced an element of pure chance into air safety. Crashes were supposed to be preventable, caused by mechanical failures or human errors. But how do you prevent a random particle from space from hitting a microchip? The cosmic ray threat challenged the foundation of aviation safety, which relied on redundancy and reliability. The revelation sent a chill through the aerospace community, highlighting a vulnerability in the digital world. For Boeing, the discovery of cosmic ray vulnerability was a nightmare. The Boeing 747 was marketed as the pinnacle of safety and technological achievement. The suggestion of a fundamental vulnerability to cosmic rays was a blow to the company's reputation. Initially there was skepticism and pushback, but the evidence was compelling. The problem wasn't a simple fix, the vulnerability was inherent in the microchips used. As computer chips became smaller and more powerful, they became more susceptible to single-event upsets. Boeing and other manufacturers had overlooked a fundamental threat from the natural environment. This exposed a blind spot in the aviation industry's approach to safety. The cosmic ray theory meant every flight was a gamble, a terrifying thought for the flying public. Engineers were now tasked with protecting aircraft from the universe itself. The crash of Air India 171 was a dire warning from the cosmos. The revelation about cosmic rays was a wake-up call for the aviation industry. Safety now had to include the unpredictable world of particle physics. Aviation authorities began to take the threat of single-event upsets seriously. Regulators demanded manufacturers prove their electronic systems were resilient to radiation effects. This led to a new field of testing and analysis known as avionics radiation hardening. The possibility of SEUs showed that digital systems have unique failure modes. The industry had to rethink the architecture of electronic systems that keep planes in the air. The tragedy of Flight 171 made the invisible visible, forcing a confrontation with a threat never considered. The focus shifted to dissimilar redundancy, using different hardware and software for critical tasks. The industry had to go back to the drawing board, rethinking the very architecture of the electronic systems. The tragedy of Flight 171 forced everyone to confront a threat they never knew existed. In response to the cosmic ray threat, aircraft manufacturers began a revolution in avionics design. The goal was to build systems that were fault-tolerant, continuing to operate safely, even after a part was compromised. Boeing, Airbus, and others invested in radiation-hardened electronics, using materials less susceptible to high-energy particles. Another innovation was sophisticated error-correcting software, constantly checking calculations and correcting discrepancies. Triple modular redundancy became standard, with multiple computers voting on critical calculations. These changes were not cheap or easy, but fundamentally changed air safety. The digital systems on today's aircraft are exponentially more resilient than those on the Emperor Ashoka. The lessons from that tragedy are built into the DNA of every modern airliner. The invisible threat from space is now met with a robust defense system. The shocking discovery following the crash led to changes that have undoubtedly saved countless lives. The skies we travel today are safer for all of us, thanks to the lessons learned from Air India 171. Today, modern airplanes are among the safest machines ever created. This safety record results from lessons learned from tragedies like Air India Flight 171. The discovery about cosmic rays forced the aviation industry to confront a new frontier of risk. It led to fault-tolerant computer systems now standard on all modern airliners. The triple redundant flight computers and radiation-hardened components protect us from invisible threats. This cosmic-level protection works every second of every flight, ensuring safety. The story of Air India 171 is a reminder that the quest for safety is a continuous journey. The mystery surrounding their final moments pushed scientists to understand the fundamental forces affecting flight. The shocking discovery terrified an industry, but also made it stronger, ensuring safer skies for everyone.